Right, sorry about that. Okay, so my topic then is the era of gravitational wave electromagnetic multi-messenger astrophysics that, as you have already heard, we have now entered. What I plan to do in this talk is to, first of all, sort of make a few somewhat general remarks about multi-messenger astrophysics and the potential and what we are learning and may learn. Come back to the event that we've heard all about, GW 170817, and mention a bit more about the phenomenology and how we're coming to understand that and what it's telling us, and put it as well into the context of some of the information that we already have about short-duration gamma-ray bursts, which are also thought to be produced by similar systems, as you've heard. Then to mention rather briefly one of the topics that we have made progress with thanks to that particular event, which is to say determination of the Hubble constant using gravitational waves, and then have a little look into the future and possibly some other areas that multi-messenger astrophysics is going to be touching on in the coming years. Okay, so first of all I wanted to put up this slide, which sort of shows the multi-messenger spectrum, if you like, in a way which is somewhat unusual. So at the top you can see the conventional electromagnetic spectrum, but I've arranged this following a slide produced by a colleague of mine, Andrew Levan. I've arranged this with other messengers that we receive from the cosmos in a way which reflects the energy of the carrier or the frequency, so that we can sort of see that in this sense at least we're sort of extending our vision. It's not just a kind of new senses, but it's also beyond the bounds in a way of the traditional electromagnetic spectrum. And so in addition to light, we have neutrinos, cosmic rays here, and newly gravitational waves forming the very low frequency end of this very large parameter space then that we have there. So the particular event that we're all excited about, the binary neutron star merger, of course, is in many ways a quintessential multi-messenger source. As you've already seen, and I'll describe some more, it emits light over almost the entire electromagnetic spectrum. It also, of course, produces gravitational waves. Very likely it is also almost certainly producing neutrinos and also as a particle accelerator, and so you know, it has the full range all in one object. However, it's not entirely the whole story, and there's one multi-messenger that's quite often forgotten, and I thought I'd just mention it because it sort of makes a bit of a story here, which of course is there's another kind of messenger we get from space and have done for a long time, which is to say meteorites. So why would I mention meteorites apart from the fact that it sort of extends our spectrum of energy even further and more dramatically? Well, the reason is, and the connection that it brings back, is that we can, and indeed do, rely on meteorites and meteoritic abundances in order to determine those solar system abundances of elements that we're trying to match when we're talking about producing the heavy elements through the S process and the R process. And in particular, those of you that follow this sort of business, or if maybe you're interested in mining asteroids, you'll know that there's a lot of very precious metals in large asteroids, which may even be economically worthwhile spending the money and going and retrieving. This sort of number, of course, is almost meaningless on a human scale. So to put it on a physicist scale, that's something like 1,000 Large Hadron Colliders. So hopefully that's got your attention, if nothing else has. So as Eleanor mentioned, one of the really driving questions which has been pushing our interest in multi-messenger astrophysics and merging neutron stars in particular over the last decades, in fact, is this question of the production of the heavy elements. It's illustrated in this particular figure here, where you see heavy elements measured in the solar system and the degree to which they can be explained by the standard slow process of neutron capture is indicated by how high they are up this diagram. And so what you can see from this figure is that at least some of the elements are pretty well explained by that slow neutron capture process, but many of them are not, and in particular the ones towards the bottom of the figure are hopelessly underrepresented, and therefore that's why you need this rapid process, which I think in particular Stefan Rosvog is probably going to tell us more of the gory details about. So this is certainly one of the very exciting aspects of multi-messenger astrophysics that we have begun to make progress with just in particular in the last year from an observational point of view. So coming back then to the event, so we've already seen what the event looked like in terms of the gravitational wave signal there at the bottom, in terms of the gamma ray signal, which are the other traces there. And those of us that were involved in making these original observations, of course, we had been preparing ourselves for this possibility for a long time. I think it's fair to say that no one expected such a remarkable event to happen so soon after the Virgo detector was turned on and joined the network and made in many ways the possibility of making these observations possible. That was a tautological statement, but you know what I mean. So how did it make it possible? Well, it certainly made us sit up and take notice when we heard that there was a gamma ray burst accompanying this binary neutron star merger, the first one that LIGO had detected. In fact, the gamma ray signal itself didn't help us. It's very interesting to understand where it came from, but it didn't really help us with the localization, as is illustrated on this plot here, which shows a substantial region of the sky, and the big blue blob is the gamma ray uncertainty, and it was very large from the Fermi satellite. The sort of small gray dots there, in fact, are galaxies, individual galaxies in the distance range determined by LIGO and Virgo, in the error region determined by LIGO and Virgo. So in fact, that was where we ended up focusing our efforts, as you can see by that zoom in there. So what did we see? So this is a little movie I made using the data from our near-infrared observations made with the ESO Vista telescope. And so you can see the host galaxy, NGC 4993 in the middle, and then the transient event starts out as a bright blue source and evolves rapidly to become red before fading away. Once we knew exactly where to look, we could then point narrow field instruments like the Hubble Space Telescope at the location. You get a very beautiful picture of the host galaxy, which turns out to be a kind of disturbed elliptical galaxy, which is, they're not super common, but they're not unusual either. So, one isn't necessarily learning all that much from the particular host galaxy. Of course, the interesting thing is all that heavy element production, which Eleanor spoke to us about and which Stefan will tell us more. Just to tie it back into the theme of the talk, the amount of heavy elements that we're talking about if we could mine this neutron star ejector is even more significant than the asteroids. So if you're speaking to your funding agencies, you may want to mention that. I don't know if this calculation allows for the inflationary pressure that mining a neutron star would bring about. Okay, so that was the phenomenon. I just wanted to remark that if the SWIFT satellite, which is our premier gamma ray burst detecting satellite, had been pointing in this direction and not on the other side of the Earth as it was, the situation would have been even more exciting. So in that sense, we were slightly unlucky. Because SWIFT gives much more precise localizations than Fermi, it would have initially, just from the gamma rays, have found an error region as shown in the red circle there, and immediately you can see that the host galaxy would have been very evident. We wouldn't have had to search a whole number of potential host galaxies in order to find the transient. This could have all been done within seconds. Indeed, SWIFT has a UV and optical telescope which would have found the ultraviolet counterpart also very likely within the first few hours, and so the situation could have been even luckier. Now, the one reason for showing this particular picture is just to emphasize a point, which is that SWIFT has now been in operation for nearly 15 years, has detected something like 100 short-duration gamma-ray bursts. Many of them, the gamma-ray signal, look pretty similar to GW 170817, but in no case do we see a galaxy like that sitting in the gamma-ray error circle. So the best we can do are a couple of instances here where there are galaxies which are moderately nearby, something like 2 or 3 times the distance of NGC 4993, but there's no clear connection for the gamma-ray burst with these two galaxies in these cases, but it's at least a possibility. But this shows us that, you know, you can stare at the sky for a long time, even with gamma-ray detectors, quite apart from supernova monitoring detectors, and you don't find many events like this. And so it suggests to me, at least, that these things are fairly rare, that you'll get a binary neutron star merger at this sort of distance, leading to also a detectable gamma-ray signal. Okay, I'll just talk briefly then about how we now know, so moving on from the gamma-ray signal, now looking at considering the kilonova signal, how that compares to the previous experience that we have from short-duration gamma-ray bursts. In other words, to try and ask the question, could we have seen similar kilonovae in previous observed short-duration gamma-ray bursts at much greater distances? Or are they telling us, in fact, that there are deeper limits that mean that the event that we saw last year couldn't have been seen in those short GRBs? And so Eleanor already mentioned there's at least one pretty compelling case now, I think, 130603b, which was the original kilonova associated with a short-duration gamma-ray burst. There have been 1 or 2 others that have been proposed over the years, and there's one there on the right. We did a survey of all of the available rich data sets of short-duration gamma-ray bursts in a paper led by Ben Gompertz, and what we found was various things. Well, there were 1 or 2 cases where it was plausible, at least there might have been a similar kilonova, somewhat brighter. There were cases where the afterglow was clearly dominant, and that's probably the majority of cases. There were also cases, and the 2 at the bottom there are illustrations of that, where there were deep observations made which rule out a kilonova as bright as the one that we saw last year. And so that's at very least telling us what no one is very surprised about, but there's variety in this phenomenon. So we've seen one, but as we see more in the coming years, I think we're going to discover that there's a big range in the population. Okay, I'm going to come on now to the later time behavior of this event. And so we've been continuing to monitor this event in X-rays, in optical, and in radio frequencies. And in particular, once the galaxy came effectively out again from behind the sun, where it lurked for an annoying 2 or 3 months, we were able to go back with the Hubble Space Telescope and see what we might see in the optical. And the answer was that we detected a source at the transient location, and those 2 panels on the left in fact show the very faint transient, so you might not be able to see it too well from your position, but trust me, there is some emission detected there. And that emission is well above the extrapolation of what you expect the behavior of the kilonova to have given. So the radioactive explosion we now think should have faded well below detectability, and so if we are seeing some light, it likely comes from a different component. And the most obvious component that it could be coming from is a traditional afterglow connected to a jet, the jet that led to the relativistic component and ultimately to the detection of the gamma rays, possibly through its effect in producing a cocoon in the ejector as the high velocity jet escaped from the ambient medium around the merging neutron star. And so we detected the optical. If we compare that to the X-ray and the radio behavior, which other people were monitoring, then you can see that we get a roughly consistent story here. We can explain the data reasonably well with what's called a structured jet, which is to say a high energy jet which has diminishing energy as you move away from the central axis. So it's maybe a sort of natural, albeit albeit a sort of physically, only plausible picture of how a high-energy jet may evolve, but it seems to explain the data with plausible parameters reasonably well. And, of course, what we're doing then is we're seeing this emission then off the axis of the main jet. And so as the jet slows down, the Doppler beaming angle broadens, and we begin to see the emission. And in particular, if there's a range of Lorentz factors within this jet, then obviously those are sort of integrated together to give you the final light curve. So this all looks kind of plausible. There's a very recent paper on the archive which I think gives a lot of support to this picture, and that is the detection of proper motion in very long baseline interferometric radio observations, proper motion of the radio counterpart. And so this was a paper by Mouley et al. You can see the two locations there, the two contours, the black contour indicating the position of the radio source about 2 months after the merger, and then the red contours another 6 months later. And so you can see that there is a significant movement between those 2 points, and that's consistent with a relativistic jet, the head of the jet producing the afterglow and moving out as the jet moves out. Okay, so I promised you I would touch on the Hubble constant determination, which has been one of the things which I think has attracted a lot of interest from this first binary neutron star merger. And this is an idea that goes back a long way. Indeed, as many of the topics that we have learned so much about in the last year, that they're sort of looking and solving and exploiting ideas which go back many decades, and this is one of them. And so the idea is that the parameters that you measure from the gravitational wave signal can give us obviously the masses of the components and the distance and these sorts of things, but crucially the distance is one which is independent of the traditional distance scale that one uses to measure distances across the universe. And so that means you're not reliant on the same old methods which have maybe systematic errors which are hard to pin down. It's a one-step distance. It doesn't rely on other calibration. And so that was the principle of the idea, and it was put into practice with this event. The data were good enough to do that. And so the distance that was obtained, as you've heard, was about 40 to 45 megaparsecs. And so that's very good. The question is, what does that mean for the Hubble constant? It turns out that this was one of those situations where, okay, it was great that we had such a nearby event to observe, but because it was so nearby, it made this particular project slightly more difficult, because the problem is, if you want the Hubble constant, you have to take the distance and divide by the velocity, the velocity and divide by the distance. And so the question is, what is the recession velocity of this galaxy? Well, that's easy enough to measure from spectroscopy, but that recession velocity itself consists not just of the overall expansion velocity, but also of the so-called peculiar motions due to masses in the local universe. And the scales that we're talking about are such that the masses are big enough that they can have significant effects, can produce peculiar velocities which are significant compared to the recession velocity. And this is a map of the local universe. The red arrow there indicates the direction that we were looking in at NGC 4993. And you can see it's not pointing at one of the very massive regions like the great attractor region there, which is the reddish region, nor is it in one of the voids, but it's somewhere in between. But nonetheless, the velocity field is sufficiently complex that it produces quite a large uncertainty in correcting and a degeneracy, basically, in terms of what the actual cosmic recession velocity is given the measured spectroscopic velocity. And so we did a study of this. We used a simulation that was modeled on our own local region of the universe. And what you find is that that uncertainty is really quite considerable. You can see there that the region of interest is in the pink band, and you can see that the peculiar velocities there of points in this simulation span something like 600 or 700 kilometers per second. And so essentially all we did was we assumed that the best we could do was take a peculiar velocity that was some kind of average and account for the dispersion due to that uncertainty. And so that was one approach. A number of people have tried other approaches. I'm going to skip over that one. The approach taken by the main LIGO Virgo paper on this topic tried to also estimate the peculiar velocity. At the end of the day, all of the different estimates that have been made come up with much the same answer, and that is that it's, the answer for the Hubble constant is around about 70. That in itself, a few years ago, would of course been dramatic progress. In the present era, that really doesn't distinguish within the range of the current sort of somewhat controversial range of possible values for the Hubble constant, which range from the sort of mid-60s through to the mid-70s. It would be very nice to be able to distinguish those, and that I think is something which is a promise for the future. But from this single event, we aren't able to do that, but we've at least proved the concept, and one can easily imagine going forward with samples potentially of some tens of such objects that you could end up with a very precise value of the Hubble constant. And of course, if we can do it at greater distances, then even individual events, the peculiar velocity corrections become relatively minor, and the uncertainties in those corrections become negligible compared to other uncertainties. So I'll just make a point in passing, which is one that has created, again, quite a lot of interest, which is that there is a strong degeneracy in performing this analysis with the inclination of the system and the distance and the value of the Hubble constant that you get out there for. Of course, we have other constraints on the inclination at some level. So if you believe the constraints that from the modeling of the jet that I've mentioned, then that can provide a restricted range of inclination angles and therefore a somewhat different value of the Hubble constant. Another way round that people have investigated is gone and tried to get independent distance estimates to the galaxy, and using those independent distance estimates, electromagnetic distance estimates, try therefore invert it and get the inclination. Unfortunately, you can't win one way or another. One of these things ends up being left uncertain, and so I think this is something for the future to look out for, and maybe in the fullness of time the gravitational wave data itself will be good enough to pin down the inclination more precisely. I wanted just to touch briefly on the issue of stellar evolution and what the observations of these kind of binaries, actually the binary black holes that have been detected by LIGO and Virgo as well, and also now the systems involving neutron stars. And the reason that that's particularly interesting is that the evolution of massive stars in binary systems is both itself very interesting, very rich, very important for understanding other classes of explosions, different kinds of supernova explosions, etc. And so just as an example in a way of the kind of complexity that is involved in getting a system which looks like a compact binary which may merge within a Hubble time, one has to start out probably with two massive stars. The more massive of the two will evolve more quickly, will undergo, if the binary is tight enough, if it's close enough together, that will lead to matter being accreted onto the secondary star from the primary. The primary then maybe becomes a Wolf-Rayet star, having lost its outer envelope. That then can explode as a supernova, so you have one supernova. That may unbind the binary and therefore you've got nothing else to talk about. But if it doesn't, then life becomes interesting. That supernova could lead to a remnant. It could be a neutron star or a black hole. The secondary is now in the game of evolving. So it goes through a period probably of being looking like a high-mass X-ray binary to us. It then starts to overflow its Roche lobe. You then expect to have a period of common envelope evolution where both the core of the secondary star and the compact remnant of the primary are within the same overall envelope. All of this is very difficult and controversial physics, and therefore, hard to make firm predictions. Ultimately, though, the common envelope phase will cease, and you then may have another supernova explosion of the secondary, which could lead to an unusual supernova having been stripped of its envelope as well. And finally, you end up with the compact binary remnant system, which may then go on to merge. So as you can appreciate, there's a great deal of complexity in all of the physics involved in that. And many uncertainties in the supernova kicks. That's important for telling us how far out of the host galaxies these binaries may finally merge, the distribution of separations of the final systems as well. So lots of interesting things, and it's unlikely that one is going to be able to look at any individual binary system and retrace its origins precisely, going back through this flow to see exactly where it came from. On the other hand, by building up population statistics in the course of time, we will start to much better understand the different channels and routes to producing compact binaries, including, as I say in the box at the bottom there, dynamical formation in things like the cores of globular clusters, where you have many massive remnants, black holes and neutron stars. They can become into binaries later in life and needn't have evolved in binaries in this way, as I've described. Okay, so for the last couple of minutes, I'm just going to spin through very briefly a quick tour of the next kind of 15 years or so in terms of some highlights from the electromagnetic side. So I think David Shoemaker may talk about developments in the gravitational wave side. I just thought I'd remind you of some of the things which are coming down the road from the electromagnetic side, which will make multi-messenger astrophysics even more exciting in the future. Well, one of them I was almost tempted to not put in because there have been some bad news recently about the James Webb Space Telescope, further delays in the launch, and so we're now talking 2021. Nonetheless, I think it's worth mentioning just because of the sheer power of the James Webb Space Telescope for doing this kind of science. Point source imaging and spectroscopy, extremely sensitive, not constrained by atmospheric absorption, which really limits us in the infrared, and particularly moving into the mid-infrared. The brightness of the Earth's atmosphere very much limits what we can do. From space, of course, that goes away, and so we will be able to get a much deeper and more impressive picture of from James Webb of these events in the 2020s. In terms of gamma ray satellites, the next one coming along, which is of interest, is the Chinese-French SVOM mission. That's scheduled to be launched in 2022, and that will be a successor mission for SWIFT, and so that's very important. SWIFT, of course, was only intended to be a 3-year mission. It's still going 15 years on, but it could, in principle, die at any time if some crucial component fails, and so we've come to rely on SWIFT very much, but it's very important that successors are coming along the line. From the point of view of the follow-up, there are many, many follow-up facilities. I couldn't review them all. The one that I suppose is sort of outstanding and possibly by the mid-2020s will be making really important contributions from the point of view of detecting optical counterparts to binary mergers is the Large Synoptic Survey Telescope. So very large 8-meter class telescope, very large camera, and the capability, therefore, of mapping error regions very, very quickly to very interesting depths. In the mid-2020s as well, the 30-meter class ground-based telescopes will come online. These will dwarf the existing 8-meter class facilities and will have even more significant point source sensitivity, because not only have they got the huge collecting area, but they also have sophisticated adaptive optics, which means that for point sources especially, you will really win there. In the 2030s, I'll just mention, those of you who heard the Future Missions session yesterday will have heard Lorenzo Amati talk about this concept for an ESA mission that's been selected for study for the M5 launch slot, Theseus, and this would be not only a successor to SWIFT, but one which went to the next level with with much greater sensitivity and much more capable for doing this kind of science in the 2030s. Okay, so I'm out of time. I'll very briefly spin through the conclusions then. We've seen that the multi-messenger era has started. There was the immediate consequence of the tight constraints on the speed of light versus gravity. There is also all of the other astrophysics that we're starting to learn, the R-process nucleosynthesis. I think that will have importance, not just from the point of view of nucleosynthesis, but feeding back in terms of the fact is, to do this modeling, you need nuclear physics and atomic physics, which goes beyond what is currently known, or certainly well known, and so will feed back into those spheres as well as stellar evolution, as I've outlined. I think detection of simultaneous gamma rays may be unusual, so that's a prediction. I'm looking forward to the first black hole neutron star system, so that will be another first to look forward to. The determination of the Hubble constant, I think, has been a really remarkable success of this campaign, although at the moment it does nothing more than say that the existing estimates of the Hubble constant are in the right ballpark. In the future, I think there's much more optimism that we will be able to potentially really help decide between these the different values of the Hubble constant obtained by other techniques. Okay, thank you.
Questions?
Okay, so the question is what range of black holes might be involved in black hole neutron star binaries, and I think obviously there is a large degree of uncertainty there from an astrophysical point of view, because we don't know the full kind of spectrum of black hole masses. That's something we've only started to learn more about from the gravitational wave detections, which have taught us that there are more massive stellar mass black holes out there than perhaps had been anticipated, and the evolution of the systems which give rise to neutron star black hole systems certainly allow for the possibility of quite a large range of stellar mass black holes, up to well, these things are always possible. The difficulty there is whether or not the neutron star gets eaten within the event horizon before it has a chance to eject much material from it. So that might not be so interesting an event.
There is no more question. Let's pick Nial again.